So far, I've shown you examples of dimensionality reduction and how it's used for field prediction. Now, I'll show you a case where we move from traditional parameter prediction to geometry prediction. For example, if we're all trying to predict the performance of an airplane wing in the past, we used to parameterize the wing like this. We used to input those parameters, but since airplane wings have extremely complex shapes, it's actually impossible for a person to parameterize all those values. So instead, we use methods like point clouds or other various techniques to make it non-parametric and then input those values. Traditionally, these methods of representing 3D have been widely used as follows. For example, if you have a 3D CAD model, you can convert it into a mesh, a point cloud, or represent it as voxels. In computer science, there have been many methods developed for learning with voxels, learning with point clouds, and learning with meshes. These methods have been extensively developed, and depending on whether you want to do classification, segmentation, or object detection, a wide variety of backbone networks have also been developed, and we can easily use them. However, when we make predictions, it's actually much more common for us to do regression rather than classification or segmentation. So if you look at typical cases using voxels, point clouds, or meshes, when converting to voxels, connecting a CNN is the most suitable approach. Because a voxel is essentially in the form of a three-dimensional image, like this, since it's in a state similar to having 3000 pixels, CNNs are the most suitable. In this case, it was an example of predicting manufacturability, and for point clouds, for example, PointNet is appropriate. That's why deep learning models in the PointNet family are developed to effectively extract features from point clouds. So, in this study as well, they trained on the aerodynamic performance of airplanes using point cloud data. Next, if your data is mesh data, since mesh data is like nodes connected to each other, it's similar to a graph. So graph-based neural networks are a good fit. That's why there has been a lot of research connecting mesh data with graph neural networks. If we take a closer, more detailed look at each of these three specific cases, this particular example is focused on accurately predicting the complex stress field that occurs during the process of bottom-up 3D printing. At this point, the training set needs to include 3D data, and when adding 3D data as shown here, you can input a small illustration of the 3D data as a point cloud and also input its cross-sectional shape as an image. So in this way, you can input the entire 3D data in a multimodal fashion, or you can input 2D data as well. As output, you get the 2D field values like this. This is a case where point clouds and 2D images were used for training. This time it is a combination of voxels and 2D images. For example, let's say there is a 3D wheel. Then the voxel values of the 3D wheel and the 2D cross-section are input. And for example, when an impact is applied to the wheel, the model simultaneously predicts the location of the maximum stress, the value of the maximum stress, and the 2D field. So we've looked at some of the traditional methods used so far: voxels, point clouds, meshes. In this 3D prediction model, understanding these representation methods accurately is the most important thing. So let's take a closer look at the advantages and disadvantages of these three methods. First, in the case of voxels, as I mentioned earlier, they work very well with 3D convolution in CNNs. And with voxels, you can represent arbitrary shapes very well. But the downside is that the visual quality is poor. It ends up looking like it's made out of Lego blocks. And it requires a lot of computational cost. That's because, thank you. Because when you divide everything into grids, into voxels, even with just 64, it becomes 64 by 64 by 64. So the dimensionality increases dramatically. So from a computational cost perspective, it's very inefficient, and it's also difficult to connect with typical engineering analyses like FEA, because it's voxel-based. Point clouds have the advantage that they can usually be easily obtained using scanning software. They're compact compared to voxels because you only need the position information for each point. And you can also represent arbitrary shapes well at the same time. The downside is that the visual quality is equally low, and it doesn't contain detailed geometric information. Because there are only points, it can't understand the relationships between the points. And likewise, you can't perform engineering analyses like F1 with point clouds. Next, with meshes, the visual quality is excellent. That's why, in graphics, 3D is usually represented with meshes, especially polygon meshes. They're also compact, like point clouds. And there's an expectation that, just like in engineering software, they might connect well with F2. Because, as I mentioned earlier, since it's a mesh, meshes can be connected to FEA. However, the traditional polygon meshes used in computer science are conceptually different from the FE meshes we use for FEA. Their purposes are different. That's why, in reality, they can't be perfectly connected. And the downside is that these are discrete and disordered elements. So in the end, in order to represent this smoothly, you need a lot of node and edge information. And those are very discrete. And actually, it's rather difficult for this method to represent arbitrary shapes. You may also encounter issues like the mesh breaking or tearing. And now the next method I want to emphasize more is implicit representation. This method is currently receiving more attention than traditional representations. Let me introduce this in more detail. To begin with, let's explore what we actually mean by an implicit representation. In many cases, this concept is more specifically referred to as a signed distance function, as I will make sure to explain in greater detail later on. When we consider a specific three-dimensional surface, the mathematical value at the surface itself is exactly 0. This value then gradually becomes more negative as you move toward the inside of the object, while it becomes increasingly positive as you move further away toward the outside environment. And it represents the distance. The farther away it is, the larger the value becomes. When represented this way, you can think of it as expressing an object like a contour map. This results in very high visual quality. It can represent even complex images very well, and it generally works well with deep learning methodologies. In particular, from a generative perspective in computer science, when creating generative models, it is common to use this kind of SDF format. Also, the information is very compact, since you only need the distance information. SDFs can represent shapes well. Now, as for the drawbacks, it's the same. It's difficult to directly connect to FEA. If we look a bit more into these distance functions, what does it mean to be implicit? Then, we can compare explicit functions and implicit functions. An explicit function is a positive function, while an implicit function is a negative function. So a positive function is one that can be written in the form y tan fcx, where the y you want to find comes out as the output. A negative function is one where x and y are both inputs and the result is 0 or some constant. That's what we mean by such a function. So, for example, the equation of a circle is the best example. So an implicit function can be expressed as x squared plus y squared equals 1. If you insist on expressing this as an explicit function, you could write it as y equals plus or minus the square root of 1 minus x squared, like this. So, as I mentioned earlier, for example, if you have something like 9, you can write x squared plus y squared plus z squared equals 1, like this. You can create a function like this, and if you do so, you can make a function where f takes x, y, and z as inputs and outputs d, which represents the distance to the surface. Earlier I mentioned contour lines, right? So the distance could be 5 or it could be 3, and if you go inside, it could be minus 5. This kind of function is called an SDF. So if we look at cases where predictions are made using the implicit representations we just learned, it goes like this. For example, when predicting the aerodynamic performance of a car, instead of inputting a cross-sectional image, there are cases where the image is converted into SDF values and then used as input. After that, the x-axis and y-axis directions are provided as inputs. In this case, they predicted the physical quantities in each direction, and they also used a CNN here. As a result, the predictions made by the CNN were very similar to those made by LBM. And this time it's 3D. If you create SDFs for each layer of this vehicle's information, it becomes 3D. So, by inputting a 3D SDF, you compress it, And then, in the compressed space, you compress it again and restore it. When restoring, the process is set up so that a flow field value like this is generated. Also, in the middle, we especially added a regression layer to the compressed space to predict the drag coefficient. So instead of inputting 3D information as traditional voxels, point clouds, or meshes, you can also input it as an SDF. This is a case that demonstrates that. Also, we can consider methods that use implicit neural representations to predict fields. Implicit neural representation, which is often abbreviated as INR, can be described more simply as a continuous mathematical function, where the specific input is provided in the form of spatial coordinate values. So, for example, if I want to predict 3D field values, I first extract some shape features from the 3D information, and then I input the XYZ coordinates of the location I want to predict. Then, the model predicts the physical quantity corresponding to those XYZ values. That could be stress or it could be pressure. So, in this way, instead of predicting all the field values at once, you predict the field values at the specific locations you want and reconstruct them. By doing this, the model can become very compact.